Hey everyone, and welcome back to another video. This time we're talking periodic table of the elements. Lots of atoms aligned in a really particular pattern, which gives us neat information and shows us trends and all kinds of cool stuff. Periodic tables actually a really cool topic. First off, before we get too far into it, I just want to say don't memorize the periodic table. You can go get a PhD in chemistry and never have bothered memorizing the periodic table. You'll learn some of it. Some of the things will stick. Like, I remember that oxygen's 15.9994. It's stuck in my head forever. You use something enough, and you will forever, ever, ever have it just stuck in your head. But it's never been of any use to me to really sit down and memorize every single element and order and be able to reproduce the periodic table from memory. It's printed in books and it's on all these posters and it's going to be given to you on handouts when you take major exams. Like, it's never required to actually memorize this thing. Please don't approach this as I'm going to memorize the periodic table. This is more about learning what's the parts. What are the trends? What are the names of some of the more common parts of it? So there's being fluent in understanding the periodic table, and then there's just trying to just rote memorization, brute force the thing. Do not brute force this thing. There's no point. I've never in my life seen a point of this. I've been a chemist for companies. I've done all sorts of things with chemistry knowledge. I've interned at NASA. I've done a ton of stuff as a chemist in my life. And being a chemist led me here to being your teacher. And at no point has there ever been any value in actually memorizing the thing. You will remember parts of it because you're going to use it a lot. Organic chemistry was really good for making me memorize certain parts of the periodic table, but at no point has memorizing the whole thing ever been of value. Okay. So what is this thing? What is this periodic table of elements? Realistically, it's an organization of the elements, and that organization is done in some clever ways, but primarily by um, by the atomic number, the number of protons inside the atoms. And this was come up with by a guy named Dmitiri Mendeleev. Mendeleev was a Russian chemist and inventor, and back in the day, he came up with this periodic law, which really says that if you arrange everything in order, if you arrange all the elements in order, you see a repeating pattern start to emerge, a periodic pattern. You may be familiar with the idea of something happening periodically, right? That's the periodic table, okay? So it's happening in a repeating pattern. Periodically, the sun will rise. Periodically, the sun will set, okay? So what he found was that periodically you would have metals that were explosive in water, okay? And those ended up becoming the group 1A elements. And that trend carries on and on and on. So the periodic table is arranged first off in periods. These are the rows, okay? The rows. And I tried to make it very obvious to you. Look at this picture here, and you see that the rows are going across. Okay, we're going across. That's a row in a table. And the periods all have the same number of atomic orbitals. Okay, so the top row has one orbit. The second row has two orbits. And the third row has three, and so on and so forth. And that's really important as far as what we do with making models of these things. That's really what we're trying to do. We want to be able to make models out of the elements and understand what they look like. That's our entire goal, and the periodic table is a tool for that. So everything in the same period is going to have the same number of atomic orbits. While if we move over to the groups or families, that's the columns. Okay, so going up and down on a periodic table is a group or a family. Okay, a family and group are pretty interchangeable. I've seen researching for this video, I've seen a few people trying to call them in different ways, but realistically, groups and families should be interchangeable terms for the columns on a periodic table. And these columns are given numbers, and they're also in the older system given numbers and letters. I actually prefer the numbers and letters, so the ones I have highlighted would be group 1A through group 8A. And I think that that's a lot easier. And you'll understand that why when we talk about the valence electrons. Um, basically, group 1A has one valence electron, and group 8A has 8 valence electrons, and it's really super easy. They have also done a version of this where it's just 1 through 18. And in the 1 through 18 version, it kind of still works out the same because turns out you have 10 of that gray zone. That gray zone is the transition metals. Okay. So you would go group 1, group 2, then you have groups 3 through 12, right? And then 13, 14, 15, 16, 17, 18. And group 1 would have 1 valence electron, 2 has 2 valence electrons. And then you just kind of skip over the transition metals. And then you're at group 13, which has 3, 14 has 4, 15 has 5, 16 has 6, 17 has 7, 18 has 8. Now, I personally prefer to call them by the 1A through 8A, and that's really what we're going to focus on. I'm not really going to talk too much about transition metals, to be honest. You're probably familiar with some of them, but their chemistry is a little bit different. How metal atoms bond together isn't something we're going to go into too much. So for the most part, it's more convenient for us to just focus on calling them groups 1A through 8A, I think. The key takeaway for groups are often more important in my mind than periods. That's because the groups have similar chemistry, very, very similar chemistry. So for instance, that first group, the alkali metals, are all reactive with water. The degree to how reactive and how violent that reaction is that as you go down the group, it gets crazier. Okay, so if you're up at the top near lithium, lithium doesn't do much. Sodium does a bit more. Potassium does a lot more. And then as you go down and down and down, it gets more and more crazy. There's a great video from I can't remember. If you just search for alkali metals and water, there's a really great video from it of them just blowing up in water. Okay, you can actually find a ton of those videos. All right. So ultimately, the other piece is that the elements in a group will have the same number of electrons in their valence shell. So again, groups become very important for us. That's more of what I'm going to focus on in this video. Periods, not so much. There's just that one bit of information about them all having the same number of orbits. The groups really are what we're going to spend a lot of time on here. So if we talk about hydrogen, hydrogen's kind of like its own little family. It doesn't really do what the other elements in that particular family do, even though it's only got one valence electron. It's because it's a gas. It's a very reactive gas. So, I mean, there are some similarities. Right below it are very reactive metals. So actually, hydrogen, being a very reactive gas, was responsible for the Hindenburg explosion. You may be familiar with that big giant Zeppelin that went up because of hydrogen gas, very flammable stuffs. And actually, that sort of energy that's in it has made it a possible source for fuels for cars. So you might have heard of hydrogen fuel cells, very, very common idea that's been being batted around since I was in college. and probably long time before of them trying to figure out how to make this work. I think they're actually beginning to start seeing this roll out finally. The alkali metals are the rest of the group 1A. That's formally group 1A. It doesn't include hydrogen. Um, that is a group of very reactive metals. If you stick them into water, you're going to get an explosion like you see in that top picture. And oftentimes they're found as salts. So they tend to form ions, often with group 7A elements. We'll get into that more in our video on bonding. But for the most part, group 1A elements, they have one valence electron, and they like to give that up and create ions, and they blow up with water. That's the fun part that everyone likes. Brainiac. It's a Brainiac video. Yeah, if you go look for a Brainiac video on the alkali metals, that is very explosive and fun. I'll link that in the description below. Alkaline earth metals, on the other hand, are the second period. So alkaline earth metals have two valence electrons. Second group, not period. They're the second group. They have two valence electrons. They're very reactive metals, and they're often found as ions in nature as well. A lot of these are really important nutrients, like calcium and magnesium are things that you get from your foods. I got a sample of foods that you would be getting them from up there. In between these become the transition metals. Now, we're not going to talk a lot about transition metals. And honestly, you don't talk a lot about transition metals because the way they bond together, metal atoms, is different than what we're going to be talking about mostly, and what we're going to be focusing on as we're making models of matter. It's more like a sea of electrons that gets shared. It's very strange. So we're not really going to talk about it too much. For the most part, you encounter these metals all the time. Like most of the time when you think of metal, you think of transition metal. Because it's what we use for jewelry. It's what we use for construction materials. It's what we use for wires. It's what we used to use mercury. Mercury is actually very dangerous. That's the weird spherical stuff, is droplets of mercury. That stuff's way dangerous and not really good for us. So we don't tend to use that one. That's the only one I can think of that is a liquid at room temperature from the transition metals. Most of them are really solid metals. Some of them are a little more flexible than others. Gold, for instance, can be pretty malleable. But honestly, yeah, you don't need to worry too much about the transition metals, except that they're that middle block of atoms and elements separating group 2A from group 3A. Okay, and technically they're the Bs. That's 1B through 10B is the group names for the transition metals, or you could call them group 13 through group 3 through 13 if you're using the newer convention for naming them. Not too important as far as what we're going to be studying, other than know that that's what those are. They're called the transition metals. They're hard and firm and ductile and all these kinds of things, and you can make them into wires and some of them, and you can make nails out of it and these kinds of things. You're never going to make a nail out of sodium metal. That's not a thing. Like sodium metal, you can cut sodium metal with scissors. Like I've literally done that for live demos where I just literally cut off a bit with some scissors. You may see me do that in class even. Now, bringing us to Group 3A. Group 3A, not terribly interesting as far as things you probably encountered in your life. The most common one's probably aluminum. You may not know this, but aluminum used to be actually really rare and expensive. Nowadays, we just think of it as like aluminum foil, and it's this thing you wrap cold pizza in if you don't have a Ziploc bag. Carbon family is a little more interesting. That's group 4A. 4A has 4 valence electrons. That's the important part. Uh, Realistically, you got carbon, which is like vital to life. Like all living things have carbon in them. Okay. Carbon atoms are the basis for making organic molecules. So without carbon, you wouldn't have life. Okay, and of course we've actually taken carbon and we've made some really cool stuff. We've made carbon fibers. I've got a friend that's got bicycles that are actually being made with carbon fiber now on the wheels and stuff. You've got diamonds, you've got graphite, you've got graphene, but also there's some really cool ones that apply to us, like silicon and germanium are used in computers. They're semiconductor materials. Okay, so you've got a ton of crazy stuff. I mean, you've even got lead, you've got tin cans, you've got all kinds of crazy stuff in this one particular family. So group 4A is pretty cool. The nitrogen family is group 5A, 5 valence electrons. Phosphorus as um, the red stuff that's on the tip of matches. You may not know that. The really important one, though, is nitrogen itself. Nitrogen makes up 3/4 of the atmosphere. 3/4 of the atmosphere. And a lot of it is not available to living things. So there's a little bit of a whole nitrogen cycle that goes on in across the world. And phosphorus is coming into us through a lot of like things like cashews and Brazil nuts and stuff. And that's a really important thing that really very important element for living things, both nitrogen and phosphorus. Um, but yeah, there's a ton of it in the air. Nitrogen's really abundant on the Earth. The oxygen family, group 6A, 6 valence electrons, is ultimately oxygen you need for respiration. You've probably seen on my little collection of gems and cool minerals and stuff. I actually have one of those selenite bars that you see pictured there. I think those are really cool. So, selenium is one of the elements in this particular group. You also got sulfur. Sulfur is that weird yellow stuff that's pictured there. That is the smelly stuff you may have seen. It's like eggs and skunks and garlic and all kinds of things come from sulfur. The halogens are group 7A or group 17. 7A has 7 valence electrons. So one away from this magic number 8. We'll talk about 8 valence electrons a lot next time. Ultimately, halogens are super volatile and reactive. They tend to occur as diatomic molecules. They're non-metal, so they tend to be gases for the most part, um, and are used as disinfectants. Fluorine is used, or fluoride is used for our teeth. Fluoride is the ionic version of fluorine, which would be the element. Um, Realistically, they're very reactive because they only need one more electron to get to this magic number 8. There are a group of elements, of course, that are already at that magic number, and those are called the noble gases. Noble gases are group 8A or group 18. Noble gases are not reactive. They do not want to react at all. There's one reaction you can get xenon to do, a couple of them where you can make like xenon tetrafluoride or xenon hexafluoride. So taking a very reactive halogen and mixing it with some xenon can, under the right conditions, make some products. But for the most part, these elements have what's called a full octet. Okay, they have 8 valence electrons. As a result, they're not really interested in bonding. Most of the bonding that we're going to look at in the next video is really centered around getting to this magic number of 8 valence electrons. And if you have that, then you're stable and you become unreactive for the most part. You're happy where you're at. So these guys having 8 valence electrons are super happy by nature. Okay, they're just not really interested in bonding with other atoms. Helium, of course, only has 2 valence electrons because it's that first shell can only hold 2. But if you looked at the valence electrons for neon, argon, krypton, xenon, it's all 8. Okay. We often use these in signs. They're very cool to look at when you like heat them up with some electricity and stuff. The also have been found as usefulness for balloons and blimps and stuff. So you've likely seen some helium balloons. You've likely breathed some helium and talked really silly with it. This is the noble gases are where those ones live. So what are some of the trends? Ultimately, the periodic table has a lot of trends. I'm not going to go into all of them. There's just too many. One of the cooler ones that's pretty easy to understand is that as I go across a period, the size goes down. So if I look at lithium here, lithium to beryllium to boron to carbon to nitrogen, oxygen, fluorine, and finally to neon, you can really see that lithium to neon, I got a lot smaller. And sodium to argon, I get a lot smaller. Potassium to krypton, I get a lot smaller. And as I'm going down a group, it's getting much larger. So hydrogen to lithium is a huge jump. Lithium to sodium not as crazy of a jump, but it's there. And the you keep growing and growing and growing. Now as I'm going down, I am gaining more orbits. So by packing on extra orbitals on these elements, you end up making bigger and bigger elements. However, there's this other effect that's going on where you're actually pulling everybody closer. You're pulling everyone a little bit closer inside the periods themselves. So within a group, I'm going down. Within a period, I'm getting smaller. So as I go down the groups, I get larger. As I go across the periods, I get smaller. Okay. The more important trend, and the one I really want you to worry about, is the valence electrons. Like I've been saying throughout this video, ultimately the valence electrons of each group are the group numbers for the most part, the exception being helium. Helium only has 2 valence electrons. It is part of the noble gas family still, but it ultimately is only got room for 2. But group 1A has 1, group 2A has 2, group 3A has 3, 4A has 4, 5A has 5, 6A has 6, 7A has 7, 8A has 8. Okay. And you can use the newer names and it fits up still. 1 to 13, 14, 15, 16, 17, 18. You just got to take the 1 off of the 13 through the 18, and you'll still see the number of valence electrons. That part's really important because the valence electrons are what's involved in bonding, and bonding is what we're going to be looking at next time. So make sure you grab some of the vocabulary from this. I will be putting out a Quizlet deck on this particular video. There's lots of terms being thrown around within here, obviously, and really focus on the valence shell stuff, being able to recognize which group you're looking at, know the difference between a group and a period. Those things are kind of important. Mostly groups are much more important than periods, to be honest. Period trends are less interesting, whereas telling you the group that an element belongs to, it tends to give you lots of information. Like, how is this thing going to react? What's the valence look like? Those kinds of pieces of information are very, very important. All right, that's about it for this video. Have a great night, and I'll see you in class tomorrow.